It's very common in mixture problems, mixtures of ideal gases, where you're given the mole fraction in problem statement, but for some reason you need to determine the mass fraction of the constituents. So for example, it might have to do with, using the first law to determine maybe the heat added. And so working with the mass fractions is going to be the way to go because mass is conserved, not necessarily not moles. So let's get started. So I want to show you step by step how to convert a given mole fraction into a mass fraction by way of an example. Okay, so this is the common situation. You're given a mole fraction, you want to find the mass fraction. And it's not just that's your assignment like it would be in high school. This is simply going to be a starting step where you're trying to solve an engineering problem such as how much heat is added as in a process of mixing some constituents together. Okay, and so here's an example problem that I'd like to illustrate how to do this work, how to change mole fraction into mass fraction. And it's a regurgitation of example 12.1 in your textbook. But I'm hoping that by giving you sort of a step-by-step approach, you can learn what you need to do a little more easily. So here's the problem statement. It says, closed system is comprised of three ideal gases. And it says a volumetric analysis reveals CO2 is 60% by volume, CO is 25% by volume, and O2 is 15% by volume. And as part of this problem, you determine the mass fractions. So I hope you see that volumetric analysis, that's the same as saying the mole fractions are given. So here's the step-by-step how to determine the mass fractions. The first thing you're going to do is on your pencil and paper, you're going to set up a table. So you cannot do this in your head, just right on your calculator. You've got to set up a table with these column headings. And so the left column heading constituent. So you've got three constituents. You just write those down. Okay. The next column is going to be the mole fraction. That's what's given to you. And in my world, what I do is I write out the units of the mole fraction. That's kilomoles of each constituent divided by the kilomoles in the mixture. Okay. And so given 0.6, 0.25, and 0.15 for those three constituents, I write that down. But I've also written down the units, kilomoles of each constituent per 1 kilomole of mixture. The next column I'm going to write down is the molecular weight. And I'm going to write the units, kilograms per kilomole. That's the units of molecular weight, isn't it? Or molecular mass, if you prefer. Kilograms per kilomole. Write that down. Next column is going to be the mass in kilograms contained in 1 kilomole of mixture. I'm going to show you how to get that. And the last column is going to be the mass fraction. That's what you're seeking to find. So you write that out. Okay, write that table out. Then start filling in the blanks. Okay, next, you should know off the top of your head, molecular weight for each constituent, CO2. That's going to be 12 plus 2 times 16. 12 plus 32, that's 44. Get that off the top of your head. CO, 12 plus 16, that's 28. Oxygen, 2 times 16, that's 32. That column was easy. Now, the mass in 1 kilomole. Okay, so notice here in this column, look how this column adds up to 1.0. So basically, you've got 1 kilomole of the mixture, 1 kilomole. So if I multiply kilomoles per kilomole of mixture by the molecular weight, you see that I get the number of kilograms in 1 kilomole of mixture. So I'm going to multiply 44 by 0.6 to get that number. Going to multiply 28 by 0.25 to get that number. 32 times 0.15 to get that number. And let's see, do the units work? Kilomoles per kilomole of mixture, kilograms per kilomole of constituent. So it's going to be kilograms per kilomole of mixture. Yeah, that works. So that unit checks out okay. We're on track. Okay, so we do the math. Okay, we sum these numbers. We sum the total masses. And so we're going to sum up these numbers to get the sum of kilograms in 1 kilomole of the mixture. Okay, there we are. 38.2 kilograms of mass in 1 kilomole of our mixture. Wow, okay. So that's the total number of kilograms. Up here, I've got the kilograms of each constituent. Wow, now that we've got this table, you see that the mass fraction is simple. It's going to be 26.4 over 38.2, 7 over 38.2, and 4.8 over 38.2. So by setting up your table and taking a couple of minutes to write out your column headings, this is a foolproof recipe for getting from a mole fraction into the mass fraction. And do recognize that that's not going to be a test problem. This isn't a test problem. It is a part of a test problem. This gets you started in solving the engineering problem. Okay, so let's add up what we have in our column. So do you see that in our mole fraction column, we add these numbers up to get 1.0? Check. Okay. Mass fractions, we need to add these up. Do we get 1.0? Yes. Check. Okay. So we've checked our work. And also observe that the mole fraction, numerically, the mole fraction is not the same as the mass fraction. So a lot of students will, oh, I thought the mass fraction and the mole fraction was the same number. It is not. Okay. Now, they're slightly different. You say, well, that's close enough. No, that I got to tell you, in a lot of mixtures, the mass fraction, the mole fractions are not close enough. So it is critical that you understand how to convert a set of mole fractions into a set of mass fractions. Important thing to learn how to do. Okay, I hope that quick example problem gives you some confidence in attacking these Chapter 12 problems. And let's see, what's the biggest takeaway is on pencil and paper, write down those column headings with some units. It's going to be a big time saver for you in the long run. So invest that time to set up the column headings in words and units, and you can't go wrong.